This video will look at hybridization. Valence bond theory involves two orbitals overlapping to form a new molecular orbital when two atoms bond. And there are three ideas you need to consider in valence bond theory. The first is that only two electrons can occupy the region where the orbitals overlap. And the two electrons must have opposite spin, which you can see here with the two arrows pointing in opposite directions. The second is that the greater the overlap of the orbitals, the stronger the bond. So if we have a longer bond, it is weaker. If we have a shorter bond, it is stronger. The third idea is that to account for the shapes of many molecules, hybridization of atomic orbitals must be invoked. That is the main focus of this video. Let's consider carbon forming four covalent bonds. Here we have the electron configuration of carbon in its ground state, and you can see that the valence electrons sit in the 2s orbital, and then we have two in two of the 2p orbitals. Now the 2s orbital is complete and it's not available for bonding. So how do we get four covalent bonds forming around a carbon atom? Well, a process called excitation occurs, which allows one of the electrons in the 2s orbital to jump up to the 2p orbital, and now we have four orbitals available to bond. It is worth noting here that Hund's rule states that valence electrons have parallel spins when separated into hybrid orbitals, and that's why all of the arrows are pointing in the same direction. Let us consider methane. Methane forms a tetrahedral shape with four equal bond angles of 109.5 degrees. And this means that the bonding orbitals need to be equivalent. Now, at the moment, we have a 2s orbital that is different to the three 2p orbitals. How can we make them the same in order to get four equal bond angles? Well, this is where we have to consider the formation of hybrid atomic orbitals. The notion of hybridization states that hybrid bonding orbitals of equal energy and size are created by mixing non-equivalent atomic orbitals. Hybrid orbitals have different energies, shapes, and orientation in space from their parent orbitals and are able to form stronger bonds by allowing for greater overlap. Now, carbon undergoes sp3 hybridization. And remember, the four orbitals we have ready for bonding are the 2s orbital and then the three 2p orbitals, x, y, and z. Now, if we take those four orbitals and merge them, we can create four sp3 orbitals, and they are exactly the same, and those are the orbitals that are used to form the tetrahedral shape we saw on the previous page. And it's called sp3 orbitals because we have one s and three p orbitals as the parent orbitals. These hybrid orbitals orient themselves at 109.5 degrees. Now, the overlap of a hybrid orbital with any other atomic orbital always forms a sigma bond. Here is a summary of the 5 types of hybridization that can occur, and we can predict what type of hybridization occurs based on the electron domain around the central atom and the VSEPR shape. So the one we just looked at was tetrahedral, which means it has an electron domain of 4 and therefore forms a hybrid orbital designation of sp3, 1s and 3p orbitals to create the sp3 orbital hybrid. Let's go and have a look at another couple of examples. We'll start with sp2 hybridization. The example we'll look at is BF3. Now, the ground state electron configuration of boron is as follows, and I've colored in blue the valence electrons. Now, if we excite these valence electrons, this is what we'll get. One of the 2s electrons has jumped up into the 2p orbital. Hybridization occurs, and we end up with 3 sp2 hybrid orbitals. When bonding, we get this shape here with 120-degree bond angles, and this is the trigonal planar shape. Just so that you know, this is a better depiction of what it looks like. It is just a little more complicated to look at all of the orbitals involved. Now, double bonds also form sp2 hybrid orbitals, and we're going to look at this in an example of ethene. So the ground state electron configuration for carbon looks like this, with blue colored the valence electrons. Excitation occurs and we end up with the second 2s electron jumping up to the 2p orbital. So we now have 4 electrons in separate orbitals ready for bonding. Hybridization occurs, but in this case we only get 3 sp2 hybrids, and we have one of the 2p electrons staying as a 2p electron. So this is the sort of shape we get with each of the carbons having the 3 sp2 orbitals around. So one of those will bond with the other carbon, the other 2 each to a hydrogen. And you can see that we have the p orbital remaining, and this is where we can form a pi bond. So the sigma bond is the sp2 to sp2 bond in the middle between the 2 carbons, and the pi bond is sitting above and below that axis. Now let's have a look at some examples of sp hybridization. We'll look at beryllium chloride. The ground state electron configuration of beryllium is like so, and if we excite this, we can separate that orbital and put one of the electrons in a 2p orbital. After hybridization, we end up with 2 sp hybrid orbitals, and the structure we get here looks like this, with a linear shape and 180 degrees, with the sp orbitals sitting between the beryllium and the chloride atoms. Again, this is a more accurate depiction showing all of the orbitals involved. Now, sp hybridization occurs in triple bonds, and we're going to look at C2H2 for this example. Again, here is the ground state electron configuration for carbon, and we're going to excite this configuration to get the 4 electrons ready for bonding, and then hybridization, and we form 2 sp hybrid orbitals, and we're going to keep 2 of those electrons in the 2p orbitals. Very similar to the example on the previous page, we have the sp orbitals forming the sigma bond between the 2 carbons, as well as each a bond to a hydrogen, and that leaves us these p orbitals to form some pi bonds. And in this case, we're going to have 1 sigma bond and 2 pi bonds. And this is another depiction of this molecule. So here's a summary of all of the different types of sigma bonds covered. So an s orbital to an s orbital to a p orbital to a p orbital, a hybridized orbital to anything. So that can include an s orbital, a p orbital, or another hybridized orbital. Finally, we're just going to look at benzene. And we know that each carbon in benzene has 3 electron domains, and hence it will form sp2 hybrid orbitals. The electron configuration for carbon is here again. We're going to excite it to form 4 orbitals ready for bonding. After hybridization, we're going to get sp2 hybrid, and we'll have 3 of those orbitals, and we'll have 1 2p orbital remaining. Now, each carbon has a remaining p orbital electron, which allows us to form the pi bonds in benzene, and there will be 3 of these. And this is what benzene will look at, and you can see where each of those double bonds is sitting is a pi bond. But we know that due to resonance, the pi bonds sit in a state that's between the two possible positions, and we can denote this with benzene, the hexagonal structure with a circle in the middle.